welcome. My name's John Gauthier. I'm a retired software engineer. Most recently worked for Siemens PLM over in the Arlington area, smaller satellite office. My idea for Halloween I came up with probably, I've been talking about it maybe for 2 years, 3 years almost. I thought, it'd be nice if they had like a big robotic spider that I could move the legs, for a Halloween project, hanging up by my front door, like to scare the kids, or maybe even fascinate the kids in some cases. And so I mulled around this for a while and finally decided, okay, I'm retired now, I got time, let's put some time into this, and see what I can do. So where to begin? I'm a beginner in most of this stuff. So I started with the leg. Let's figure out what I can do with the functional part, the part that's going to move, and the rest will follow. So I had no idea how big the spider was going to be when I started. All right. So I started experimenting with some designs. I started with servos, with these micro servos and balsa wood, because it was going to have to be light. But then you can see how the design here where I had two servos, one for the inner knuckle and then one for the outer knuckle, and I was using this fishing line to operate the knuckles. And that didn't really work out too well. Was having mechanical problems with it. I went and enhanced it a little bit and added another joint to here. So I started using my 3D printer to print the joints to make it a little bit more durable and easier to work with. All right, so, and then I also went from a fishing line to a bowstring here. So it's got one servo here to operate the inner knuckle, and then there's one on the other side for the outer knuckle. All right, so the bowstring operates the outer knuckle, and the inner joint is just a parallelogram type assembly here. And then to operate the hip, I have a piece of music wire attached to a servo here that moves the hip up. Problem is, those servos are fragile, and I broke about 3 of them before I finally decided, there's too much force on the servos and too much weight. It's just not going to work. So I kind of moved on to the next phase, which was to go, to stepper motors, but also to go with a fully blown 3D printed design. Because one of the things I found about a balsa wood is every time you put a screw to it, it softens and it indents, and then the stuff doesn't fit anymore, and it's just, balsa wood is light, and in some cases it's strong, but it just is not very durable. So here's my 3D leg, the 3D printed leg in Google SketchUp, which is free. So the inner knuckle motor goes here. The hip motor, once again, will be out here that will be controlled up and down with an actuator. And I couldn't get a motor on the leg anywhere. They're just too big. So I still went with with a bowstring that connects that 2 points here, 2 opposing points on the outer knuckle to operate that.
So the bowstring works against gravity?
Well, you can see it here. Not against gravity. It's just opposing points on the joint.
It'll push or
so when this armature here rotates back and forth, then these 2 points rotate back and forth to operate that.
Like push pull.
Just like the human body.
Yeah. And then the hip, to control the hip joint up and down, I've got this little actuator bar right here that's attached to this third stepper motor. Plus, you can see I've got all the stepper motor hardware in here as well, which, let's see, so basically shows you what we were seeing there in a diagram. Nothing to show here. There are limit switches. Let's see if I have those attached here. Yeah, at each extreme of, let's see if I can turn it upwards. At each extreme of the rotation of the stepper motor, there's a limit switch. You basically can hit one. You're at the end, you stop the motor, don't break anything, you hit the other. So I got a clockwise and a counterclockwise limit switch there.
And you just find these small steppers were a little bit more powerful or durable than the servos? Or?
Oh yeah. You get more torque, and they're just easier to attach things to. These are there's a 5-volt version of this and a 12-volt version. You want to use the 12-volt version to get the extra torque.
And that's a geared stepper or just directly
No,
to a
it's
stepper?
No, it's geared, I think,
I don't know. I think it's
Yeah.
yeah. Yeah, I thought they were.
All right, this is one of the problems I had to overcome with the bowstring, is when you have a bowstring line that runs over this middle joint to operate the outer joint, the line A1 to D to A2, if you rotate the outer portion down, you can see the bowstring now travels a greater distance around this intermediate point. So every time I would bend the joint, the string would be tight, and every time I extended the joint, it would be loose, and sometimes it would come loose and not stay attached. So I kind of gave up trying to come up with a mechanical geometrical solution to that. So my solution was just to make the diameter D as small as possible. So basically, I've just got a little like 16th inch diameter brass rod there that the line goes around, so that to minimize that effect. But that was one of the problems I had to deal with. This is the spider leg control circuit. I have an earlier version of the design right here. I had these designed this in KiCad, which is free software for circuit design, and had the boards manufactured by a company called Oshpark. Nice thing is that manufacturing these boards is really, really cheap because they do it in big batches. You get the boards this size, 3 of these manufactured for well less than $10. So that's sort of a great resource. So the core of every board that I've got in here just about is a PIC microcontroller. So this particular one, we've got power and programming connector here feeding in. I've got clockwise and counterclockwise limit switch inputs coming in here on some of the IOs. And then I've got a connector over here for communicating with the main controller and the other, basically the main spider controller via a I2C interface. So the serial data serial clockwise there. And then there's a calibrate line here too. I'll explain that later. And then finally, the outputs of this right here goes to the motor. These are your phase, your individual phases of your stepper motor. It goes to the motor driver. Let's see. So this is pseudocode for the code on the PIC, which is written in C. And basically, it's a 3-state machine. When you power up, the first thing it does is go through what's called range calibration state. So what it does is it's waiting for a button press, but while it's doing this, it's basically monitoring the inputs that's coming in from the main controller in an I2C communication buffer. And it's basically seeing analog values that are coming from the glove, which are essentially voltage across resistive flex sensors. Right? So the idea here is you sit here and you want to find the full range of resistances or voltages, if you will, as you bend the fingers. So here's this maximum flexure and here's minimum flexure. So it records the highest and lowest values while it's going through that loop. Then I press the calibration button and moves to the next state, the stepper range calibration state. Now, what you'll see is both knuckles of each leg will now go through their full range of motion until they hit a limit switch, and they'll back off, hit the other limit switch. Now I've got a range of steps that corresponds to a range of resistance or voltages from the flex sensors for each leg. So that helps me keep everything, calibrated where I don't overrun the end and don't get any weird stuff going on. So let's see, and then after it finishes cycling those motors to the extremes on each knuckle, it automatically goes to the normal operating state. There's basically, from now on, it's just going to read the I2C buffer, the measurements from the flex sensors. All right. It's going to convert those flex sensor inputs to the desired step position based on the ranges I found. And based on the difference, it's going to calculate the direction it wants to go from the current step position, and it sets the step motor speed and direction according to that difference. There's a bit more in there that, for example, one of the things I put in there was there's an algorithm for proportional integral control. So it kind of smooths the motions of the leg out a little bit. So as the knuckle approaches its final position, it will actually start to slow down and it won't overshoot. So it's not very twitchy when you do that. Okay, let's see, next. All right, so as I was building this out, I started figuring out what I can actually do with a certain size leg and a certain type of stepper motor. Now I had to start basically deciding, okay, how am I going to fit all of this into the frame of a spider? So then I started building multiple legs, putting them next to each other and figuring out, well, can I fit all the hardware and the wiring in there without getting anything snagged? So that's what you see here. And in this, over here, you can see in the early stages, I was driving the legs directly from the glove. This is a prototype of my data glove. You'll see later where I changed that design for remote control. So moving on, I went to Google SketchUp and finished out the rest of the frame, the base and the frame, the skeleton. Basically, you have the 4 operable legs right here. The challenge here was, and I wish I kind of had done this differently, maybe next year I'll modify it. One of the problems on these stepper motors is they come with fairly short wires to the driver board, right? And I was unwilling to cut those permanently and extend the cable, so I had to mount the control boards as close to the motors as possible. And this really kind of created a mess because there's a lot of stuff packed into the end legs. If I modify this design in the future, I want to put longer wires in there and pull those boards back into the middle of the spider and leave myself a lot more room here, because it's really a pain to take them apart and make adjustments and put it back together. Let's see. You can see positions for speakers here, because I wanted to put sound in here. There's a center stack for mounting my leg controller boards. There's 6 of them in there. There's, for each leg, the inner and outer joints are operated by 1 leg controller board each. Then for the hips, basically I've got a vent sensor in the wrist of the glove that controls the hip position, but it's all the hips raised and lowered together. But we've got 1 board to drive legs on the hip joints on the right, and then 1 board to drive the hip joints on the left. So that's why I need 6 boards.
So was that for a twerking spider?
What's that?
The hip joint movement?
I just going through as much realism as I can get to. All right, so here's the spider without the skin. As things started coming together, you see you got the 4 functional legs in the front, and then basically the static legs in the back. And then you can see the little control stack. We'll see it when we get closer. See, you get an idea of just how crowded things were getting, in the middle there, especially around the legs. And then I have the eyes are wired to a Raspberry Pi. These LEDs you see on the front, come out the front. Okay. So there's a closer look at the innards. There's the leg and hip controller stack, where I've got power here. I've got the motor connections out on this side, and this is all on an I2C interface, so they're daisy chained together on the opposite side. You can see the wires on the opposite side. All the leg controller boards are daisy chained. So I've got the master controller board here. Talks through the I2C interface to this stack. So there's a master, on the 6 legs. Also in KiCad, and I had a manufacturer with Oshpark power distribution board. These are 12-volt step-down converters, 12 volt to 3 volts. So we've got the red line, are 12 volts going out to the stepper motors, and then I've got 3 volts coming out of the power distribution to all the electronics. The main controller is also responsible with remote control. So there's a RF transceiver plugged into the main controller board to talk with the unit on the glove side. Of course, there's my speakers. I got on SparkFun a Noisy Cricket audio amplifier, nice small little amplifier to use with the Raspberry Pi. I also needed a USB sound adapter here that routes into it. This battery pack, this is an older design. I went from vertical to putting it underneath because it occurred to me I need to get to the power switch on this thing. So I actually found it putting it underneath instead. And then the Raspberry Pi that I use for playing sounds and for lighting the eyes comes here.
Your ARC transceiver, is that Wi-Fi or?
No, it's just basically like RC control type, you know, the same type of chip they use in RC planes and drones. They're pretty cheap too. And in fact, one of the design constraints here was I didn't want to blow a whole lot of money doing this, so the boards are very expensive. Are not very expensive to manufacture. All the software I'm using is free. The stepper motors are really cheap, you know, less than $5 each. So you can get away with a lot, you know, if you're willing to make some sacrifices in your design. Okay, this is the main controller that I talked about earlier. Once again, it's got a Microchip PIC microcontroller in the center of it. The RF module doesn't use I2C, it uses the SPI interface. So there's a SPI interface connector right here to the RF module. I've kind of got a little semi-standard power and programming connector that I use. It's got a jumper on it so I can tell when I'm programming or tell when I'm just supplying power. I don't really use all of these anymore because I changed the design and I only use one calibration line that goes to the whole stack of leg controllers, and that sends the signal, daisy chains the signal to all the controllers in the stack. I didn't mark the individual uses for these GPIOs that I pulled out, but these GPIOs are for, well, there's the calibrate signal, there's the signals that go to the Raspberry Pi and the Raspberry Pi's GPIOs for selecting the sounds to play, and there's the motor signals that to operate the gantry motor to lift the spider up and have to come out of these IOs right here. And well, now we'll get into that. All right, so here's the glove hardware. We've got an RF transceiver, just like the one on the main controller, that plugs into the board. The remote control board for the glove is here. And you can see on this side, I put a little extra hardware in there I needed to be able to adjust the resistance of the flex sensors a little bit, because that's kind of a little bit variable, so I needed to be able to tune these. Other than that, there's a lithium-ion battery inside that box, and I put a battery manager right here to help with the power. And then there's also a 3D printed design for the other hand that has 3 switches on it. One switch, actually 2 switches to select sounds to play, and then one switch is a toggle that raises and lowers the spider of the gantry. And the flex sensors, I don't know if y'all have ever seen them, but I've got a sample here. You get these from Adafruit. Unfortunately, these are one of the more expensive components. This one 4-inch flex sensor is $13.
How many did you need on the glove, total flex sensors?
I had 4 long ones and 4 short ones. I'm sorry, 5 long ones and 4 short ones. Because I had the wrist sensor as well. And let's see, this is, did I just go backwards? No, I didn't. This is actually the glove board. You can see there's the trim pots that I put on the board. Once again, the PIC and an RF connection, power and programming connection, and then the IOs for the switch come in through this connector, and then all of the flex sensors come through this port right here. So the way that one of the things I had to do here was the PIC can only measure up to, at least the low power PIC that operates at 3.3 volts, it can only measure voltages up to 2 volts. So that's the other reason I had to have some kind of tunable pot in here each circuit here is a voltage divider, and I need to be able to adjust the pot so that the maximum flexure would generate a voltage right at about 2 volts. So that's the extreme of what the PIC can measure.
You couldn't source the resistors with a lower voltage, you could have, I guess, but you could have regulated a 2 volt or whatever supply for the flex sensors, and then they would now be limited to that voltage.
No, that's one thing I hadn't considered. But,
Okay, but
anyway. Either way, yeah, I could have put a 2 volt supply
Regulator,
in the
yeah,
regulator in
okay.
there, so that's a good idea. And then, not much to see here, because you can see the gantry yourself, except that the motors, and this is before I put a box on the motor, because one of the problems with this motor is it's very noisy. And so I kind of put a box around it and put some rubber in there on the mounts, and it's still kind of noisy, but, you know. And then, of course, there's the wire you see coming down here to the motor controller for the lifting and the lowering. All right, that's taser wire, which you might find is very, very useful. It's very thin, very hard to see, so kind of at night it kind of just looks like part of the webbing. So that's one of the reasons I chose taser wire. But as I pointed out, it does tangle easily and you can't easily, so you got to.
You get caught in it like real spider web.
Some of the things let's see, one of the things I didn't bring is also had a battery pack up here, and it had some 3D printed spiders about this big. And I drilled a couple of holes in the make like eye sockets and put an LED inside. So basically, you turn the switch on, and you have some little spiders hanging out of the web with glowing eyes. So I didn't bother to bring those because that's a little bit messy to set up.
So John, the power for the gantry is coming from the spider?
No, the power for the gantry is coming from this lithium-ion pack right here.
Okay, but so the taser wire, what's the purpose of the taser wire?
Well, so the spider has power, has one of these power packs, and the gantry has one of these power packs. But I'm not using remote control to go from the spider to the spider gantry motor. So I needed to run the wires up to
Control, just signals.
and I don't want the spider driving the gantry motor up, not the power driving the motor on the frame. So it's not cutting into the spider's power. So it kind of splits the power distribution. Okay, and so this is where it was finally coming together. Went to Joanne's with Mike's wife and sister and picked out some fabric, and they're the ones who basically did all the hard work on the fabric, because I don't sew.
And I will chime in that was interesting because my wife decided to mess her shoulder up. She was planning to do all the sewing. So my sister ended up having to do all the sewing, and she was not real happy with all of the problems because it took her quite a bit of work to get that fabric wrapped around there in a way that looked like it should.
Yeah.
We were wondering about the silver in that. Did you guys paint that on?
No. That's the way the fabric came.
It's hard to work with.
It's very difficult to work with.
Is that any name for the fabric type, or?
What's that? No, it's
It was something they set out for, I think, for Halloween. Was it a Halloween fabric?
I'm not sure if they explicitly set it out for Halloween, or we just managed to find it.
We just
you know.
happened to, I mean, they spent hours at the fabric store
Yeah.
going, looking at.
Because we didn't find something that was light and fairly, and fairly thin, and had some furry look to it, so.
So it's furry and metallic-y look, or?
Yeah.
Okay.
It's a polyester or something, probably?
Or something.
It's
That'd
soft
make a
as well,
scary
I'll tell you
looking
that.
coat
I mean,
or
it's-
something.
But that
It's a
furry
very
stuff,
soft- it's a
that
very
little
soft-
furry, the furry
That
material
silver's
comes
not
off and
stiff
it
at
gets
all.
bits
It's-
everywhere. His sister was complaining about
Every-
that
every
it's
head-
all over the
yeah.
kitchen floor.
It's like a pet.
And the big problem, the big problem is right here in the legs. Any place that there's an extra force in the legs causes the stepper motors to slip. So if the fabric binds in the legs, that's a problem. So we have lots of trouble with that, trying to get something that fit around the legs. It wasn't too loose, it wasn't too tight, didn't snag. So that was a real pain. And let's see. There's the final product as we set it up, and I put some skeleton down here beneath it, put some webbing in there, and put all the fabric over. The trick was, I wanted a cover like this so you could raise it up where you could just barely see it, just the legs, and have it lower down, right?
And he treated it like his familiar you know, where he was controlling it with his hooded cape, with his hands. So it looked really cool, because, I don't know, anyway.
You role played with it.
Yeah, he role played with it,
So
so.
this is just one, I guess spandex glove glued on top of another with the flex sensors in between. Okay.
Yes,
And
yes.
Does the glove fit?
Yeah.
The glove fits.
The glove fits, the spider is innocent. I couldn't come over quick enough, sorry.
That would be Michael Jackson controlling.
Yeah.
All right, so let's see.
Need help with that, John?
Since we just started it up, it should be, well, yeah, if you will. It should be in the calibration state right now. Now go to the back of the spider and push the button on the right.
The run button?
No. No, the button.
The contact switch?
Yeah.
The other way.
All right, I got it. I'm ready.
So now it's going to the next state, calibrating the legs. And I already can see I got one knuckle that's stuck.
Still look awesome.
Hey, Ray,
Yeah.
can you slide over just a minute? Thank you.
That way. Hey, Ray, did you move it back?
The bag.
John, can you move closer to it so we can get you in
Oh,
with it?
right, go to the back and flip the switch that says run stop to the run position. The Raspberry Pi is not running. Okay, so let me move over.
Oh, we're gonna have to, it's gotta boot up.
And I'm gonna have to wait for a while for the Raspberry Pi to come up. Be able to. And
Somebody's familiar with
but
that.
I can raise and lower with this third switch.
So how do you unstick your knuckle? Do you have to like gently undo?
Yeah, I just got to get in there and play with the fabric until it doesn't bind anymore. Well, I'll know we're getting close when we see those two eyes go out, because the reason that just two of the eyes light up is that it turns out that the GPIOs that I use, the Raspberry Pi, those two LEDs are hooked to GPIOs whose default state is on, and the other one two have a default state of off. So, but it also gives me a nice, interesting clue that hey, the Raspberry Pi is almost up and running now. All right, so give it a few more seconds here to finish moving. You see, I can lower or raise all the hips together. Although it helps if you can see it has a little trouble raising and lowering the legs, the hips, if I have the legs extended, because that's extra weight. So let's see if we can get a sound play. May not be fully up yet. This is the calm mode, as I call it. Sandy mode.
Can you talk
Question
about
is,
the
can anyone
recordings?
identify what that sound is?
Yeah, tell them about how you got the recording.
I want to
Oh,
see if
okay.
anybody recognizes it.
Sounds like a Nazgul.
The dragon ride in Nashville. And the other, the calm sounds are a combination of stuff that I found online, including sounds from aliens. Oh, I'm sorry, from Predator. And doesn't always respond to my sound selections. You can see my legs now coming off.
You can do the legs individually?
Yeah, so here, so let me just bring it close so you can see it. Now I'm losing, Mike, can you come over here and, somebody's come over here and slide the fabric a little bit on the leg if you can.
Oh, it's coming loose?
Yeah, just see if you can slide it back up.
You could also just take it off so they could see it.
Oh, it's coming way down. I see what you're saying. All right, I know what I'm trying to do
I said take it off.
now. You just like it unclothed.
It looks really cool. They're robot people. They want to see their robotics.
That's good.
I'm
Okay.
just saying.
All right, so
I tried, guys. You know.
we'll do this where you can see it. controls the hips.
So on your fingers, does it recognize the individual joints on your finger?
Theoretically, it would, but in truth, I probably could have gone with one long 4-inch flex sensor because I guess my knuckles just don't bend enough. You know, I can't bend my knuckle knuckles on my finger in such a way where you can actually see it. But it is wired. There's a short flex sensor for the outer knuckle and a long flex sensor for the inner knuckle, but you really can't tell.
Hard to see.
So,
Because they move so naturally that way.
Yeah.
It seems.
He didn't have to program it to mimic natural movement.
anybody want to give it a try? No? Okay.
Sure.
Well, I'm sure somebody.
Carl's adventures.
Why not?
Carl.
Come on, Carl.
And you're losing that, there it goes, go ahead and take it
Oh,
off.
yeah, just let it go.
Let it
Just
come
let it go.
You did a lot
It's
of
gonna
work
ruin it for us.
printing
Now
that
we're
thing.
gonna know it's not real.
No, it's not.
Tiny little piece.
Okay, it came off before,
So just,
it wasn't me.
hopefully this will fit your hand.
Now, if the glove fits.
Look at that. The glove fits. So if I just,
So I'm just going to start over the calibration.
Okay.
So you got the glove on firmly?
glove on firmly.
All right, so we're going to go ahead and reset. And for some reason, I think I've got feedback in there where it triggers one of the GPIOs when I reset the calibration.
It works. Doesn't like a reset.
So now, flex your fingers to the full range of motion. All right? Flex out, out, flex back, flex out. And bend your wrist up and down.
And down.
All right.
All right? Now, don't calibrate now according to, let's wait for it now. Wait, it's
Okay,
not,
wait.
it's still in,
It's doing its thing.
it's not in the state yet where it'll operate.
It wants to teach
Yeah.
Carl what to do. Who's controlling who?
Then move over so you can see what you're doing.
All right.
Since you have limit switches on the stepper motors, why do you need this calibration?
Basically, maybe it's a little bit of overkill, all right? But the stepper motors will slip over time if you apply any kind of weight, you know? So there's a lot of things in here that I did that may not seem to be necessary, but it's,
And I think if you keep flexing those sensors, probably the resistance is going to change a little over time.
yeah, that's the other thing too, is you can measure each of these flex sensors to their full range, and they don't all match exactly,
Yeah.
you know? Plus, there's variations in the glove, you know, and how the flex sensors fit against the fingers. So I basically tried to eliminate having to mess with any of that by making everything adjustable.
Are the flex sensors linear?
I
What
have
angle?
not, approximately, I have not actually, you know,
So you
watched the resistance across a full range to see if it's
So
true.
you don't have a slope multiplier in there, you're assuming they're linear.
I'm assuming they're linear, they seem to be.
You'd hardly notice, right? If you got the ends fairly good, then if it was a little bit out of whack, who would you?
How you
really
gonna tell, yeah.
Yeah.
And there's the switch.
All right.
Unless you wanted to like write,
There's the,
do like handwriting.
So there's the, yeah, you can.
Yeah, there's the motion
there's
seats
motion
now.
on it, just one,
you can get the one joint if your fingers are really.
not old and non-flexible like mine.
You force it a
You
little
don't
bit.
have a separate muscle.
That's pretty cool. That's
There's some people.
pretty darn cool. All right, and then you got the sounds too.
So it's not real responsive to the sound. Now, yeah, just click one. There you go. That's the angry sound. But you have to wait for. One of the things I found is it doesn't seem to be real responsive to the switch inputs. I think because of the Raspberry Pi's too busy to process the interrupt. You know, when
Too
it's
much
playing
going on.
sound. So.
Oops.
No, he's putting in.
Oh.
That's a top. That was a top.
Oh, it's a toggle, all right.
So it's up, stop, down, stop.
Little Miss Muppet.
It can't support its own weight, so you don't wanna
And then the other
put
one's
it all the way down.
is the crickets, the sleepy.
What was that Woody Allen film, James in the room with the tape machine?
All right. So Go ahead and flex them all the way in and pull your wrist back.
All right,
Okay, hold it there. No, yeah,
all right.
this one's not coming in, but that's fine.
Yes.
When I shut it down, there we go.
Now it's in its rest.
Yeah,
It's in its dead bug position.
right. I needed to do that because if the legs are extended, but I put it down,
Good.
it might break something. So
All right.
that's it.
Can you talk
Nice.
about how long you spent doing it?
Well, I have no idea in terms of hours, but it took me about a little over a year once I really launched into it and started.
Enjoy retirement.
Yeah.
These are your,
And then do you know about how much you spent, do you think, like on materials? I know you 3D printed a lot of it yourself, but you had to,
It's really hard to calculate. I'm
Yeah.
sure I've spent several $100s on it,
yeah.
all told. Because, I can only print segments in my printer 6.5 inches long max. So I've got lots of screws in there. I've got like 700 screws in there that I bought online from Fastenal, to put this thing together. Those will add up.
And didn't you say that that was really the most expensive part, was just buying all the little bitty screws?
It's hard to say. I mean,
The boards add up too.
like $12 per flex sensor. Well, for the long flex sensors times 5, they're right there. You're at $60, right? Just for the long flex sensors.
Why screw it together? Why not glue it together?
Oh, that's it.
I don't think I could trust a glue to stay fastened, and I need to be able to take it apart again for mistakes.
Yeah, with some breaks.
There was a lot of trial and error. I had to put something together, try it for a while. No, it doesn't quite work. I go back
Longer, needs to
into
be shorter.
yeah, longer, shorter. The mechanical part is hard for me. I have the programming and electrical part down, but the mechanical part.
done a pretty awesome job
Yeah,
on the
did a great
mechanical
job.
part. I mean,
And so you had this out at Halloween. What was the best response you had from?
The funniest response I found was this little, probably kid between 3 and 4, but closer to 3. He wasn't scared at all. He walked right up to it and watched it, all right? And then when he was done, he walked away, and as he was walking away, I heard him mumble, "I'm not scared of that spider."
But you said that there was a breakdown between the ages of like different age groups tended to
Yeah,
respond differently.
the little kids were not scared. They
Right.
were fascinated. The 10-year-old kids were the ones that didn't want to get near.
So you said you were a software developer before, and so how much of this did you actually have to go learn, like the CAD drawing, the mechanical stuff?
A good part of it, I mean, I've got the C programming down, but a lot of the stuff I learned from scratch. I just started using Google SketchUp. Hey, here's something for you, let's start playing with it, I found out about KiCad from Tommy. My friend Tommy has experience with KiCad. I went through the tutorial and figured out, now I do have electrical engineering degree, so I did have a leg up on the circuit design, but I didn't know how to use KiCad, and I had to figure out how to do that and how to get the board into PCB design and send it off to Oshpark, get it manufactured. I don't know if any of you guys do any of that sort of thing, but you can do this very cheaply, with free stuff and very cheap boards.
$5 a square inch for 3 boards, normal rate, but when you're want it now, then it's $10 a square inch. If you want it, they get it in about 8 days.
Yeah. And I love those PIC microcontrollers. They are, you can do, you can do digital I/O, you can do better analog inputs, you can generate PWM signals, I2C, a SPI interface.
And that was a lot of time that I know you spent, because I was involved in some of that, was just figuring out how a PIC works. And each one of them is a little bit different as you go up. But they've got them from the bare bones, simplest little microcontroller.
8-pin?
Yeah,
all the way
up to,
like 40.
up to 40 or 80 pin packages that are just, will do all kinds of things. So you kind of have to pick your price point and what your application is. But they all generally work about the same.
But even the PICs are fairly cheap. One
Yes.
PIC is maybe $5 or $6, for the lower mid-range ones, and they're a little bit more expensive for the upper ones. But
Did you ever consider Arduino stuff?
what's that? Arduino?
Yeah.
No, I hadn't considered it. For some reason, I just latched on to Raspberry Pi and PIC, you know, and I kind of love rolling your own when it comes to the hardware. But yeah, I understand that with an Arduino, you can probably do a lot of the same stuff.
Yeah.
And I had to learn how to do surface mount soldering. I got some training from Tommy as well.
So you didn't use a shop to solder it, you did your own soldering?
Yeah, I just, basically, what I get from Oshpark is a bare board. All right, and then you buy the surface mount parts. Man, you talk about, you know, having to have fine motor control and a good magnifier, good illuminated magnifier to do surface mount soldering, especially when you look at some of these boards, the real fine pitch between the contacts and the PIC. Yeah, I spent lots of time trying to desolder solder bridges.
There's I guess a couple of people have done, you know, the ovens where you have a temperature profile. It's kind of like, well, it's a modified toaster oven pretty much. And so you can use solder paste, stick all your parts down, stick it in the oven and have it go through whatever profile you want. So you don't melt your parts or your boards, you don't want to get it too hot.
Yeah, very
Well,
good.
you know, and that's, I'm sure you know, that's kind of the big, there's always the decision with any of this hobbyist stuff is, sure, I could buy expensive stuff, you know, and I could buy entire modules off the shelf.
Yeah.
Well, what's the fun in that, right?
Oh.
But, you know, I see what you mean. I don't know how much one of those ovens, do you have any idea what those ovens
Well,
cost?
most people
Well,
go,
buy a $50 oven
Oh, really? Just
or a
$50 for?
$25.
Yeah, you can toast it yourself.
Well, and really, a lot of, like the oven I have, it's a little underpowered, and I noticed that the thing runs, you could just almost wing it, because I tend to run a little long in my soldering profiles, because it's late getting up to temperature. So if you had a temperature sensor, whatever, a thermocouple or whatever to measure you wouldn't even need a controller. You could just sit there and just about watch it. You know, bring it up to about 100, let it go, and then bring it up to whatever the peak is, 230, 240, for whatever solder, leaded or unleaded. And, you know, if you're not, I'm sure if you were doing big production, you'd be worried about having an exact profile. But for this type of stuff, it's gonna work. And
Well,
it's
if I
a
build bigger
big-
boards, I might go that route.
yeah, it's a nice thing, because the stencils are easy, and now Oshpark even has a direct link to Osh Stencil. If you don't have access to a laser or whatever to make your own stencils, which I do, and I still use Osh Stencil. And so you can get your stencils made out of Kapton or stainless for, you know, 10, 20 bucks. You know, especially if you're gonna do 10 or 15 or 20 boards, it's kind of nice.
Yeah.
But hand soldering's not that bad either.
Is that to apply solder paste or?
Right, yeah, to screen on, use a credit card or whatever to screen on your paste. But anyway, but hand soldering's not bad. The best thing I ever learned, Dale Wheat, I noticed, when I first got into this 20 years ago, I had him do some of my surface mount stuff, and you know, for a steady hand, the biggest thing I watched him sit there, and he planted his hand on the table. I was trying to do this when I was working with tweezers. The best trick I ever learned is you slap your hand down, and now suddenly you can work with this stuff, you know, under a decent magnifier, and there's not as much to shape. But all you need to do is lift your hands off, and you'll, oh, this is really tough. But anyway, that was the big secret there, since he's not here to tell you that. Anyway,
I
that's
don't know
my-
about you, but with the fine pitch chips, even with your hand on the table, which I've learned to do myself, it's still very hard to get that chip position.
Yeah, you know, I tend to just grab often, I use typically small outline. I hate like the QFNs and stuff. I've done some of that. But like the small outline chips, I grab them by one leg with my little tweezers, and I can get them right in position. And it works pretty well. I don't do that much of this stuff. There's probably people that do a lot. I do, you know, every couple of months I have to do 24.
What they should do is come up with a PCB design where the contacts are actually below the surface of the board, so when you drop the chip in, it just falls into place.
There you go. Well, if you had access to a laser, I thought about that, you could make a template where you could drop your ICs, you know, and they would match the boards. If you've got a shaky hand, you could have like a template where you could, you know, suspend over the board and then position devices that way. And that's an option. Or build a pick and place machine as your next,
There you go.
Spider placement.
Yeah, there you go.
Well,
Pick and place spider.
anyone else?
What were you thinking that you said you might want to do modifications to for next year? I mean, because obviously you've done this much work. I mean, you want to keep running with the spider theme. What were
Yeah,
you
well,
thinking of doing for like next year
Trying
to it?
to overcome some of the difficult problems like the fabric being snagged. One of the things that I had that I didn't explain, it was back in the design, the leg design, these white pieces you see out here on the end. What I was doing there was experimenting with different ways to kind of mount a sheath on the outside of the leg. Instead of having fabric sitting loosely over these ribs, I was thinking I can attach the fabric to these sheaths and then have segments of them, not one long piece of fabric, but segments of fragment of fabric with maybe a split here that you really couldn't see very well. That would keep this material from binding up onto the leg and preventing the joint from moving. So that's one of the things to overcome. The other thing is, of course, as I pointed out, all of the motor driver hardware being packed into this small space makes working with the whole thing very difficult to take apart, adjust, and put back together. So if I come up with some extensions to those stepper motor connections, move the boards back further into the spine.
Were they a weird pin spacing? Were they like 2 millimeter or something, or on the stepper motors? Were they like not standardish?
Well, I don't know if you see these here. You want to say weird? It's just kind of funny because I just went and purchased some prefabricated connectors and wires that I thought would do the trick, that just basically hook up an extension so I could move the board back. When I got them, I found out that they were smaller than these. Now,
Oh, maybe
these apparently-
JSTs then?
Or 2
Yeah,
millimeter?
JST PH. So basically, I guess what I got was 2 millimeter, and these are 2.5,
Yeah.
I believe.
Yeah.
So,
10 inch versus.
Yeah.
Yeah.
and I haven't been able to find prefabricated wires out. It's like, now that I know I need 2.54 millimeter, maybe I can find it.
Do flex circuits, I see Oshpark does flex, right?
What's that?
I was looking here, it looks like Oshpark does flexible circuits, so
That
you
might
could
get
just.
expensive.
Oh, well, I mean, it's already cheap for them to manufacture. I wonder, but they're probably betting on economy of scale, right? Lots of people do these kind of circuit boards. How many people are doing the flexible ones? That's probably gonna be a.
It looked like similar price rates.
What's that?
It looked like similar rates per square inch, so if
Really?
we could,
Wow, well, hey.
yeah, a little longer lead time.
But that
Well,
can.
they run it when their board's full, right? So they just wait to get enough orders to fill a board.
I don't know how often they do.
If you're
That's
half
why the
inch
lead
by
time's longer.
10,
Hmm.
Yeah.
that's 5 square inches, that's now $25 for that cable. You might do better to find jumper cables and gizmos.
Yeah, or I just bite the bullet and permanently cut the
Yeah.
wires and.
Or what you
solder
could
it
do
back.
is make a little adapter that, just make an adapter wherever at the end of your stepper motor cable that's, 2 millimeter, get the little pins or whatever, and then that adapter board, of course, since it's about a quarter of a square inch, and that's literally what Oshpark will charge you. They'll charge you a fourth of $5, what, about 25, and no shipping. So if you need 3 of those boards to play with, I've had orders that are that size, literally, that the shipping has probably cost them $2, but they've mailed it to me and given me the boards for like $1 or $2.
Yeah. Well, here's the thing, is this is probably just overkill again, that I was trying to go through too much effort to avoid cutting the wires and then soldering them back or putting them back. Might as well just do that. Save yourself, do a little extra effort, do a permanent modification, and what is it gonna hurt, right?
It gets bad doing
You hate,
100 wires.
you hate modifying something that you can't unmodify, right? That's kind of the
John,
principle.
she had a question. Yeah, let me talk about is the fabric binding at the top of the knuckle, or is it bunching underneath?
At the bottom.
At the bottom, it's bunching
It's
underneath?
basically bunching under the bottom there.
So it's not snagging on the top at all?
Sometimes if it's taut from here all the way to the end, sometimes there's a little extra force on the top. But mostly the problem's on the bottom.
So if it's on the bottom, as long as your fabric is staying the same. You can tack the tips.
I'll pass the fabric around so you guys can
You
fondle
can
it.
tack
no?
the tips. It's cool.
Don't give it to Ray, don't give it to Ray.
Now, and then when it comes to that inside joint, just take a piece of this soft plastic and then attach it sewn onto that so that that slides. Because what it's going to do is going to make it stand out just a little bit. You know what I mean? As long as it's flexible, because what's happening is the fabric itself is too soft. So, no, you stiffen it.
Need covered in spandex, so it
Stretches.
There you go.
Anyway, if you've got an extra piece of fabric, I could try playing around with it, but yeah, you just, because all it would be just like a strip, maybe this long and about that wide of
Ray,
fabric.
you need a roll of stuff.
And then
I do
that will bend because it's soft.
Nice blankie.
But the plastic will keep it from bunching up inside that joint.
Yeah, that's just, I'd have to devise some way to attach the plastic.
Sew it.
That's
You sew
kinda
it.
like, where does it fit in design, right? You kind of have to look.
You just sew it. As long as you've got your tips.
No, where does oh, you're saying that the
It's a
bendable
needle
plastic
stuff, yeah.
piece is not attached to the leg, it's attached to the fabric.
That's cool.
Okay.
Yes.
I see what you're saying.
Yeah.
That's
I noticed
And then
there's,
if you tack the tips of these legs to the end of your actual plastic, then that's not going to fall off and that's going to keep things in place. And you can tack it 2 other places to make sure that it stays in place in that plastic.
That's
right
okay.
there.
That's
So
something
that
I-
keeps everything kind of still flexible and covered and loose and you don't have to redesign a bunch of stuff.
But if I work on this for next year, I'll consider that.
Okay.
For the younger kids that aren't afraid of it, I think you can add like a silly string sprayer in the back. And then probably get-
Yeah, you see, add another switch to activate a new leg.
Web thrower.
Yeah.
Yeah, or launch out a whole bunch of little bitty spiders and shoot them out the front.
Well,
Candy
that-
spiders.
Well, that is one of the considerations I had to think about. One of the things I thought about with those extra spiders
ask Becky
is
to tell me.
I would have some boards that would come out from the top and hang further out.
Yeah.
So when people walked up to look, I could hit a switch and drop a bunch of spiders on it.
Yeah, especially when they decide they're not scared about this, something sudden.
That's
But at Halloween, you have to worry about bigger kids
That's what
getting
will happen.
scared, running away, knocking over little kids on the sidewalk.
So.
I don't know that.
I'm gonna go-
I wonder if they had that.
This is.
Yeah, that felt good.
Oh,
There's a needle sticking in it.
that's
Definitely
what
makes
I-
everybody needs
That's where my
You have to know
sister's
which
getting
part
it.
to
I
rub.
wondered that.
That's funny.
Don't show your needles.
It's right, don't you?
No, sure.
Good thing he didn't poke somebody in the face when they were rubbing it on their face.
Yeah, that's right. I was gonna take it and put it over, make a little hairpiece out of it. A little emergency cornea
Emergency,
surgery.
emergency toupee.
I've been there.
What's the robot club for? Emergency coordinator surgery.
Who else?
Didn't think to have everybody sign a waiver before we passed it around.
Hey,
That's right. Did
John?
anybody try to
John,
do the kids?
let's keep it up for a few minutes where John is going through the makerspace to see if there's anybody who might be interested in coming seeing this. So I'm going to stop the recording. Thank you very much for this presentation. It was very, very well organized, and I'm sure a lot of us would
That-